Hello everyone. So the next type of problem is analyze the continuous beam by stiffness matrix method. Okay, so you can see here there is a beam in which end A is fixed, B is having a hinge support, C is having also a roller support, and at D there is a overhang. So CD is a overhang. So uh, D is a free end. Okay, so when you get the overhang problems as such, so what you're supposed to do is convert this overhang and show it as a moment here. Okay, so in that case, it would be A, B, C. So instead of the CB, okay, so 60 into 2. So this is going in clockwise direction. So convert this moment into 60 into 2, that is 120, and show it here. Now this is the final form of the figure. All right, so now as usual, first find out the P. Now see here, P is nothing but capital P is nothing but P, that is rotation, if there is any moment at AB or BC. Okay, so there are two joints here, so BA or AB and BC. So in BAB there is no moment here. All right, but in C you can see here, in C there is a moment, in BC span at C there is a moment which is of 120 kilonewton meter. So what I'll write here is P is equal to, now there is a moment here, so P is equal to 0 first. At AB it is 0, at C, in BC it is 120, so it is 120. Okay, then find the reactions. Okay, so apply the formula, that is kinematic indeterminacy is equal to 3j minus r plus m. Okay, so then this is the fixed support, reaction at the fixed support is 1, 2 and 3, then roller support 1, here also roller support 1. Okay, so put it in the formula, so 3 into 3, joints are 3, 1 2 3, 3 joints, reaction is 5, that is 1 2 3 4 and 5 reactions, then plus members, that is 1 and 2. Okay, so it is 9 minus 7 is 2, so kinematic indeterminacy is 2, that means it can rotate in two different, it can move in two different direction. Okay, reaction is the opposite of kinematic indeterminacy. Okay, so here in first, it is a fixed support, so it cannot move in any direction. Okay, it is fixed completely. So this kinematic indeterminacy is 2 now, so that means there is a hinge support, that is a roller support here. It is restricted in vertical direction, but it can still rotate in the second direction. So this is 1. Okay, this is kinematic indeterminacy is 1 here. Okay, next, similarly in C. Okay, in C, so this is, it is restricted in C direction, there is a reaction in C, but it can still rotate in second direction here. Okay, it can still rotate. So here this is 1, kinematic indeterminacy is 1 here, and second would be here. Okay, next as usual find the fixed end moments. The fixed end moments would be MFAB. Okay, and then in the third diagram write it as fixed all this supports, that is A, B and C. So MFAB, MFBA, so it's eccentric support, put the formula WAB square by L square. Then MFBA, okay, WA square B by L square. Okay, then MFBC, WL square by 12, MFCB is plus WL square by 12. Okay, so once you get this, next find out PL. PL is nothing but the sum of moments at the respective joints. So P moment at the loads, because of the loads. So at B, okay, you can see here B is connected. So first BA, BC, okay. So MFBA plus MFBC. Then at C, so it is MCB, MFCB. So first write the formula, then whatever we've calculated here, substitute here and then simplify. So PL would be minus 66 and plus 106. Okay, so we got P also and PL also. So next is finding the stiffness matrix. So when you're finding the stiffness matrix, again the same thing should be applied. That is, first apply unit displacement in coordinate direction 1. So we are going to apply unit displacement. That is, theta B should be equal to 1. Okay, so first draw the diagram like this, A, B and C. Okay, fix A and C. All right, only you have to release the joint where you're applying the rotation. So in that case, theta b is equal to 1 radian here. Now, and always this radian should be in the clockwise direction. So you're applying the moment in clockwise direction. So apply this. Now, when you apply this moment, so AB part, okay, when you apply this moment, you can see here, first BC span goes downward, okay, it bends like this, okay, and when this bends, again, when this pushes on top, this moment, when it pushes on top, it is AB, that means AB goes upward. So this is upward and this is downward. So in this, now the beam is said to be in equilibrium. All right, so once you draw this deflected shape of the beam, you can see in the red mark, it's deflected shape of the beam once you apply the load, that is rotation. Okay, next is you have to mark the displacements here. That is, first mark this as K. Okay, so it is K1. K1 means stiffness matrix, that is stiffness displacement in direction 1. So, okay, then K2. K2 means displacement in direction 2. Okay, next, because you're applying rotation in first direction, the impact is 1 here. Here also, in K2, the impact of 1 at K2. So K1 means in first direction, K2 means second direction. Then you are applying the unit rotation at one direction, okay, first direction. So 1, here also impact of 1 on 2. So it is K21. Okay, see, all the rotations should be, or the movements should be clockwise. Okay, all right. So once you write this, next is K11. Okay, solve for K11. So K11 and K21, these are the unknowns. So K11 is equal to 2EI by L. Then it is like MBA. So it is 2 times theta A. So theta A is 1. Then B is the moment you are going to apply. Okay, so it is starting from BA. So B is the first joint. So because B is the first joint, you have to multiply with 2. So that's why it is theta A plus 2 theta B plus, next, the second joint, that is MFBC. So MFBC is 2EI by L. So 2 times theta B plus theta C. Okay, then solve this. Okay, again you can keep it in the decimal form, that is K11 in 7 by 3, keep it in decimal form, that is 2.33. Again, why to keep it in decimal form? Because you can directly solve in the calci. Okay, similarly K21. Okay, so K21, find out K21, that is 2EI by L. Then moment in K21 is only CB. So CB is 2 times theta C plus theta B is equal to this thing. Okay, so K21 is half EI or 0.5 EI. Okay, all right. So here also I have not written here, you can just write 7 EI by 3. Okay, next, similarly, now come to the second direction. So you have found out both the unknowns here, 1 and 2. Okay, come to the second diagram, that is unit displacement at C. So unit displacement at C is, again, only at C you have to apply the rotation, that is A, B and C, fix all A, B and C. Then apply the unit rotation at C, that is theta C is equal to 1 radian. So now K12, okay, again see here, K1 write as usual. Okay, before that what you'll do is just draw the deflected shape. So when you apply this rotation theta C like this, so what it tries to do is it tries to push BC upward. So this is the deflected shape of the beam. Then as usual, BC and CB are moving, they are rotating. So mark here K1, K2. Okay, so this is the first direction, K1, K2. This will be fixed. Now you are applying the rotation at in coordinate direction 2. So this is 2 and this is also 2. All right. So K1 coordinate direction 1, K2 coordinate direction 2. All right. Then because you are applying the rotation at second direction, that is C is second direction. So 2 here and the second place would be 2 here. Okay. All right. Next is find this unknowns, that is K12. So K12 is nothing but it is MBC. So MBC is equal to C, only whatever is rotating, the deflection shape, only that you should consider. So here nothing is affected in BA. So you have to, you should not consider that. So it is BC only. So it is 2EI by L. Okay. 2EI by L. Then 2 times theta B plus theta C. Okay, this is 4 meter actually. All right, don't write 3, it's 4. So 2EI by L, then 2 times theta b plus theta c. So theta c is again, we are releasing this joint. Okay, so theta b is fixed here. Okay, wherever we apply the rotation, that joint should be released. Okay, so other joint should be fixed. That's why theta b is 0 and this is theta c. Okay, so we get the value k12. Similarly, find out k22. So k22 is nothing but 2 ei by l, then cb. Okay, so cb is again 2 times theta c plus theta b. You can write it in order only. So theta b, wherever the joint is there, this you have to multiply with 2. All right. Okay, so once you solve this, write the formula, then solve this. Okay, so in the formula, again write it as stiffness matrix equation is given by K delta is equal to P minus PL. This is a stiffness matrix equation. So again, write this matrix properly. Okay, it is K11, K12, K21, K22. Okay, uh, okay, so you can see here K11, first row, first column, second row, first column, then here also K12, first row, second column, second row, second column. So writing this is very important. Once you write this, next is delta 1 and delta 2 are the unknowns which you are supposed to find out. Then put it in the formula P minus PL. So P minus PL is, we've already found out P is 0, 120 minus PL. So minus 67, this becomes plus. So minus minus plus, this is minus. Okay, then you can solve this, just substitute the values. All right, this simplify this portion. Okay, now here again I've done it manually, this portion. Again you can do it directly in the calci. Okay, keep it in the form like delta 1 delta 2, this complete matrix inverse into this. Okay, so again same thing, it's all done manually. Okay, now again how I've done manual is determinant of this 7 into 3, 7 into 3, 1 divided by 7 into 3 minus 1.5 into 1.5 I've written here. All right, next this portion, so it is inverse now. 3 becomes 7, 7 becomes 3, and this matrix, these becomes minus 1, minus 1.5, minus 1.5. Again the last one, so it is row into column. Write this row into column. So 3 into this, 3 into 66 minus 1.5 into 13. Then similarly, minus 1.5 into 66 plus 7 into 13.33. Okay, this is a manual method. You can do this method, or more easiest method is the doing it in the calci. I have told you before. Again, how to do it in the calci? Choose start in the calci, choose mode, then press 3 times. You will get mat. Okay, use that mat option here, then shift mat. Okay, press shift 4, that is mat, and in that you have dimension. So in that dimension, choose 1 dim, dim, choose first option dim, then it will ask how much is the size of the matrix. So right, first this is 2 by 2 matrix. Okay, and insert all these values here. Again it is in fraction. Don't keep it in fraction, keep it in decimal. Solve this and keep it in decimal. Things becomes easy. All right, then what you'll do is take the next one. Again you have set mat A, next choose mat B. So in mat B, so that is again again it will ask for dimensions. So it is 2 rows, 2 by 1, 2 rows 1 column. Then write all these values. Okay, then now the matrix is all fed, that is matrix A and matrix B fed in the calci. Then what you're supposed to do is take the calci, now multiply, again shift matrix, again third option is there, mat. Okay, so shift 4, you will get matrix option, press 3. So then in press 3, then you put it as mat A inverse mat B. Okay, mat A inverse mat B. If you multiply directly, you will get the value, that is 28.80, and theta C is minus 1.07. So you'll get both the values. So once you get the values, that is matrix, that is theta B and theta C, next is you have to use the slope deflection equations to calculate the final moments, that is MAB. Okay, MAB, that is fixed end moments plus 2EI by L. Okay, fixed end moments plus 2EI by L. Then again, A is the first term, 2 times theta A plus theta B. Solve this, substitute the value of theta B, okay, and solve. Next, similarly, MBA, fixed end moments plus 2EI by L, theta A plus 2 times theta B, because theta B is the first term, all right. So next is just simplification. Similarly, come to BC, fixed end moments plus 2EI. So B is the first term, 2 times theta B plus theta C, 0. All right, so theta B is also exists, theta C also exists, so you have to put both the values and solve. And finally, MCB is fixed end moments 2EI, theta B plus 2 times theta C minus 0. So MCB you get, all right. So the check is MBA and MBC should be equal and opposite. So it is 78.5, here it is minus 78.5. So it is, one is plus, the other is minus, all right. Okay, so the main important thing of stiffness matrix is finding out these k values, substituting this properly here, okay, and then directly multiplying this in the calci. Okay, all right. So that's all for today. Thank you.